Swayam Prabha. Digital India. Educated India.
So now let's get back to a very important principle which we are discussing. The principle of virtual work is, so we started it last week. So where this concerns about the system, a particle, bodies or system of bodies which are under equilibrium. That is our present study, the statics. Bodies are under equilibrium, there's no motion. And so if you have those kind of things which we have been studying, is that this brings in the work as well as the virtual work. So last week we have seen how the work can be calculated, force multiplied by the displacement, that's the usual definition, by dot product. And so similarly, we also have seen how if there is a moment, so moment multiplied by the angle of rotation, small angle of rotation, will constitute the work of a moment. And then we also have seen that that is simply, say, here. So this is what the principle of virtual work says. There are several things which you need to understand, appreciate, and be careful. So usually we use this symbol delta R for virtual displacement, whereas this delta R is for the actual displacement. If the body is actually moving, then we use this delta R. Otherwise, as far as this virtual work is concerned, so the difference between this delta R and this virtual displacement is that this delta R is unique. That means that if you have unbalanced forces in this one, so the particle will actually move in a certain direction, okay, given by the velocity at that point, right? This is the actual displacement, whereas this one is only a hypothetical or virtual displacement. So that means that this point is under equilibrium. We just displace it in any arbitrary direction. So this is delta R is, so I'll just write it here. This is actual displacement if there are unbalanced forces. Whereas this is a hypothetical displacement, or we call it as virtual displacement in any direction. So it can be in any direction or maybe any angle orientation. So this is an arbitrary or a hypothetical or virtual displacement. So it is a matter of a mathematical displacement. So the particle is actually moved if the particle, okay, with a big if it moves through a delta R like this one, then what is the work done that is associated with that one is given by the forces multiplied by delta R, which is the dot product. But so that means that we also can displace it in this direction or in this direction or in any direction. So delta R can be either like this or A prime can be anyway. Okay, so I hope you have understanding that. So this delta r can be any orbital displacement, but however, there is a certain restriction that is applied on this one. So this is any delta, any displacement, okay, satisfying the constraints imposed on the system. Okay, so for example, here in this system of bodies, so for example, there is this point C here, cannot have any displacement other than having a horizontal displacement. So it's only allowed to have a horizontal displacement, point 1 either this way or this way, not 1 either this way or that way. So because this is, so this delta r here is important, okay, satisfying constraints, and here we call them as kinematic constraints. So this is the only restriction that is imposed on this virtual displacement. Virtual displacement can be anything as long as it is satisfying the kinematic constraints. So that means that it can be either moving this way. So for example, if this A is here, so it may be, so this link can rotate. It cannot leave this point, right? This point A is supposed to stay here, and it may have a rotation at the best. Okay, and this point, if you want to give a displacement, so then it has to have only horizontal displacement. Okay, so now this is what we have seen. So here, so that means that let's go from particle to rigid body here. In particle, we said that this is the one. So if you go one more step here, so since delta r is constant for all the, we can even take it out and set it like this one. So if this is true for all displacements delta r, then what all we can say is that this in the bracket has to be 0, right? So if it is true for all delta r, then that means that sigma fi has to be 0. So which means that, which is very, very trivial from the point of view, we know it already. So that means that this virtual work principle does not really give anything a special advantage as far as a single particle is concerned. So same thing is true with one isolated rigid body. So if you have one isolated rigid body, so then what we do here is similar to this one. So sigma fi. So that means that if this has to move, the points have to move here by a certain displacement here. So you can see that they're all having a displacement. So that means that if all the points are having horizontal displacement, again sigma fi x is 0. If all the points are having a displacement in the y direction, so it is sigma fi y is 0, because that delta r in x direction, delta r in y direction can be taken out. And if they have a rotation, so then every point seems to be moving in a certain arbitrary direction, but however, they are all constrained to a certain degrees of freedom. So probably we'll see it a little later. Yesterday we have maybe we have seen that also. So for example, we said that any orbital displacement. So any orbital displacement coming to each of these points, okay, each of these points, for example, if you want to say like this one, if this is what you want to say here, so this delta Ri is actually can be brought to a certain, say, orbital displacement plus a certain angular velocity. So this we will appreciate it a lot more later. So that means that if it is going through a rigid body in 2 dimensions, if it is moving, it can be shown that it can be written as a translation with one of the points and a rotation about that point. Okay, so that means that any body is moving, any body is rotating and moving, so can be shown to be it is having a translation and a rotation. Okay, so that's we are going to discuss it a lot more later. But if this is going to be substituted into this one, so it looks like this one. So which we can put it as so interestingly here, if this has to be 0, so then what we have to say is that since these are all arbitrary, so in fact this is even a small rotation delta omega. Okay, here since we are talking about small things, so we will say small rotation. So what we can appreciate here is that if this is according to the virtual principle, if this is 0, so then what it will turn out for a single rigid body is that this is summation of all the work done by all the forces, which can be written as Fi dot delta R and Fi dot delta omega cross delta Ri. So which says that what is this one? So let me just spend a minute on this one. If I will write it here again, delta Rg here. So true for all delta R and delta omega, then we can say that this is independently 0, this is independently 0, which means that sigma Fi has to be 0, and the delta, if you can take it out, then Fi dot okay. So this delta Rg, which is here, has been taken out because that's common, and so it is like this one. And so similarly here, delta omega can be taken out. It's a dot product, right? Triple dot product, which can be taken out here. Sorry, this is a lost here. Okay. Okay. So, well, anyway, so it's a cross, so that may be there. So what this is? What is this saying? So this is nothing but summation of all the forces, okay, in any direction is 0. And so similarly here, this is what? Fi cross Ri cross Fi, if you take it to be, then it is nothing but moment of all the forces about G. We are talking about G. So about G is 0. So that means that the virtual work principle, which says that the sum of all the work done by all the forces for any rigid body moment, if it is 0, which is nothing but this one, okay, which is nothing but this one, which is nothing but what we have studied, saying that sigma of all the forces, external forces acting on the body, should add up to 0. And so similarly, sigma of, you can take this, so, okay, say the moment of all the forces acting of external forces is 0. So this is nothing really very, so there is nothing very much different from these two. So actually the advantage comes for So sure if I have given that. So let me, I'm not sure if I had given it last time. So the principle is, now we are under, the principle is, this is from the book only, the virtual work last time I must have given this one, but I'm writing it. External active forces on an ideal is 0 for any and all virtual space. I'm using this principle, I'm telling it, but I'm just writing it for the sake of completeness. The principle says that the virtual work done by the external active forces on the mechanical system in equilibrium is 0 for any and all virtual displacements consistent with constraints, kinematic constraints. Okay, so this is the principle which I've been saying it, but I'm just putting it down here. So which says that for a particle it is very simple, and for a rigid body also I showed that rigid body under equilibrium will obviously will be, the virtual work will be 0 for one rigid body under equilibrium. Okay, but we said that for these two, so there is nothing any really decided advantage. Either you apply the basic equations of equilibrium of forces, or whether you apply the virtual work principle. So the real advantage comes from the system of bodies. There are a few points I need to tell you I'll come back and tell you. So a system of bodies, we have seen a number of examples of a system of bodies. So we will take up a simple system like a simple pendulum or a double pendulum, or even easy thing, or even something here, which we have done it a number of times here. So this is system of connected bodies. This is a system of just two bodies, or so these are all, this is system of two bodies connected by a rope. Number of examples are here, 1, 2, 3. So 3, or you can even say here, this is So for example, this is another example. This is called a 4-bar mechanism. So where we have a number of links, 3 links here, which are connected by hinges here. And then if you give a similar angular rotation for this one, so the rest of the bodies also move in according to the some geometric relationship. So here, so you can say that if there is a weight here and there is a weight here, okay, and so if this is under equilibrium, so then we know that if you give a small moment here, so the arbitrary displacement here should be consistent with the constraints. So that means that you can make this body go here, the prime, and so you can, this moves by a certain distance here, and this moves by a certain distance here. And so for this arbitrary displacement, so we know according to this principle, so the work done by the whole system. So here, there are many forces which are acting on this one. So one is the tension, and the other one, obviously the mains are the weights, as well as there is some normal reactions here on this body. Okay, so there is a normal reaction by this one on this one, and but as well as there may be tensions here. So the advantage of this principle is that if you take these things separately, if you take this body A separately, that's what we do in the usual equilibrium equation. So if you, in your regular thing, so we do a tension here and a weight and a normal reaction. So this is for A. And for B, so you have a tension. So this is, so you solve for this one including T, you solve this one including T. So then you make the equilibrium of this one, you find equilibrium of this one. So then you eliminate the variables, or if you want certain variable T, so you can manipulate the equations so that you get all these things. But in any case, so you'll be taking all these forces here. And similarly, you take all these forces. For example, to get the T, so then N will be required here. So with certain theta here, so there is a thing. So if you apply this virtual work principle, so then what we can do is that we will move this by a certain displacement delta R. So if you move this by a certain displacement here, say delta R, then this also will be moving by S. We know that this is inextensible, so you have the same delta R. So the thing is that if you consider the work of all the forces here, so then the work done by the forces T is 0, right? Work done by T is 0 because T is an internal force. So T is acting here and T is also acting here, and T undergoes the same amount of displacement at A as well as at B. So that is one thing. The other one, again, so the constraint is that this A has to move along the inclined plane. So the work done by the normal reaction is 0. So the only work done by N is also 0. So that then the only work done here is by what? The component of T of W1 and component of, well, That's all, right? So if you add these two, then it will be 0. So essentially the work is done by the component of W1 along the inclined direction and component of W2 obviously along the vertical direction. So that's all. So that means that you will get one simple equation connecting W1 and W2 together with the arbitrary displacement delta R. So you have to see how you can eliminate it. Okay. So there is also another term here by active forces. So the active forces here, what we mean is that the work done by the work contributed by the forces here. So the active forces here are only the component of W1 and component of W2 here, because this is the only one which are actively contributing to the work. The other forces like T and the other forces like N, they are not active forces because they are not contributing anything to the work. Okay, so I hope you understood the active forces. Okay, so like this, so we can make an equation. I'll leave it. This is a very simple one. I'll leave it to you. And we can relate the W1 and W2 by simply applying this one. Okay. And then you know how to do it, right? Essentially, what you need to do is that if this is moving by a delta R here, okay, what is the component of W1 in this direction? So the component of W1 is W1 sine theta. It's very simple here. So W1 sine theta in the negative direction plus W2. See how beautifully and elegantly it comes. So W1 sine theta delta R plus W2 into delta R is 0. So which essentially means that W1 sine theta. So this is the one which you should appreciate. So that means that this has to be 0 for all arbitrary values of delta R. Okay. So which means that then the one in the bracket has to be 0 at all times. So that is the equation. So that means that W1 is W1 sine theta, which you know from your very basic school calculation, right? So this is, so you can, so in a very single shot, you are able to appreciate the relationship between W1 and W2. Otherwise, what you should have to do, you have to analyze this free body diagram, you have to analyze this free body diagram and eliminate T. So, and then you calculate the relationship between W1 and W2. So now you can see the power of this principle, that you can, for a very complex system of forces, so you can really get very, very simple equation. So it's really a very beautiful principle. So let's also do this one. There are more bodies and maybe the geometric relationship is a little bit more. So let us take that. Okay. So let us try to get what we would like to, a little bit geometry, but not really complex. So I'll draw this again. I'll draw this. So we will, it's a very favorite example for me. I keep drawing this. So we have a simple crank and connecting rod mechanism. This is called AB is a crank, this is a connecting rod, and this is a piston or a slider. So this you see very often in our mechanical system. So this is equivalent to a mechanism which you see in the piston moving up and down in an engine, or you can even see it in the reciprocating compressor. And you see this is very, very often, even in your lathe machines, even if you're shaping machines, you would have seen. So, okay. So now our interest is to find out. So let us say this is. So let us say this is a length R here and this is a C here. So we would like to find out a relationship between if there are weights acting W1 and W2 here, and then so they're trying to bring the mechanism down here, and then you require a force here so that you require a certain theta. You maintain a certain theta here, right? So let's so if you want to find out relationship between W1, W2 and F, most of the time, right? We are not really interested in the what is the kind of reaction, normal reaction you have here, or what is the kind of the reactions here. So AY and AX, maybe sometimes, but not most of the time. What is required here is what is F you require here, so that this W1 and W2, so the total system is under equilibrium. So this is under equilibrium. So if you want to do that, so what we need beautifully is we can just apply this principle of virtual work. So in the principle of virtual work, of course, if you there are many internal forces. What are the internal forces here? So for example, at B you have, so there are internal forces at B, even at A, this will not move anyway. So for example, which are the forces, which are the active forces here, which will do the work? So if you see here, these forces at A will not move at all, so they will not do any work. The force at N, which is perpendicular to this one, is perpendicular to the moment of C, and so it will not do any work. What about this Bx and By? So this Bx and By are the internal forces. So now I wrote the free body diagrams. So these are the free body diagrams. So the force here, the Bx By, which is an external force on this one, will be also acting on BC if you draw the free body diagram, but in the opposite direction. So if you consider the work done by both the links here together, then the work done by the internal forces is zero. So because if the point B moves, so this will do a certain work, and whereas these forces will do the opposite work, and then together they will be adding up to zero. So the work done at B is adding up to zero. So what is the work done then? So well, there is a W1 here and W2 here. So what is the displacement which we can apply here, consistent with the constraints of the system? The constraint of the system is that it has to rotate here. This point C has to move. So this one. So what we can do here is that the only thing has this can rotate by a small angle here. So let us say if this is theta, then this part is delta theta, and then here, then it will be like this. So B moves to B prime and C moves to C prime here, And then, so obviously, some of them will do the positive work, some of them will do the negative work. And so this is only one possible degree of freedom. This system has only one degree of freedom in the sense that it can rotate a little bit and all other things will follow. So we need not apply anything other degrees of freedom. So this system is known as one degree of freedom of system. So what is degree of freedom of system? So degree of freedom of system is that how many variables you require to describe the configuration of the system completely. Okay. So here only one is enough. In fact, if you say the angle theta is the degree of freedom, or on the other hand, somebody even say that, well, okay, so this distance from here to here, which we represent by x, so that is also can be a degree of freedom. So once you define x, everything else is fixed. So that means that essentially there is only one degree of freedom, whether you call it theta, whether you call it x. So you have only one degree of freedom. Okay. So if you, so going by our conventional approach require a lot of three equations here, three equations here, and then it is going to be, well, you can solve it. It's not impossible. Only thing is that it is a lot involved. So we would like to apply this principle of virtual work. We'll apply the principle of virtual work. So how do we do that? So the work is done by, let us do one thing. Let us simplify this one. Let us simplify this one by having only simplify the system. An M and an F. Okay, there are only two forces. Instead of all these things, let's simplify. Only two forces. One is the moment, the other one is an F here. Okay, A. So in this case now, so what is that which we need to? So what we do is that we will give a small delta theta here. Let us give a increment theta, which is a delta theta. Okay. So if you give an increment in theta, then the work done by M is simply M into delta theta. So what about F here? So F is, so if you call this as X, so work done by F is F into delta X. Okay. So the total work is, this is the virtual work. Okay. Is M delta theta F. So we would like to find out what is the F required to counteract this moment M. So we, according to the principle, so this is 0. So total work done. So what we require is that what is X and theta. So we, here it looks like we are having two orbital displacement, delta theta and delta X. So which we can really write in terms of theta. So for example, X can be written as R cos theta plus L cos phi. So where this is phi, this is L, and this is R, right? So this is, so if I want to, interestingly, I'm including many new variables, And if I take a small variation x, delta x, so I told you this follows the same rules of your differential calculus. So you are differentiating, trying to find out what is the small delta x here. So it is, you differentiate this one, so r sine theta delta theta and L sine phi delta phi. So I'm introducing too many. So that means that now I can write this in terms of this one, but then I have introduced delta phi here. So to do that, I need another small relationship here. Is that a relationship, geometric relationship? Geometric. So that is L sine theta is, sorry, r sine theta is L sine phi. So this is the relationship. Okay. So what, again here we can go for differentiations or trying to find out relationship. So it's r cos theta, delta theta, and L cos phi, delta phi, right? So we have all the relationship now. So there is a 1 here, there is a 2 here, and a 3 here. Okay. So can we, what is that which we require? So here, if you go for this one, so m delta theta and f delta x is given by this one minus r sine theta delta theta and minus L sine phi delta phi. I will replace it here as r cos theta by L cos phi and times delta. Okay, so I think now what I'm heading for. So here, what is that which I need to do? I can take delta theta outside, then I got a relationship between. So the whole thing can be written as multiplied by delta theta. And so if this has to be 0 for all delta theta, the 1 in the bracket has to be 0. Okay. So I hope you understand this one. So the geometry here is very simple compared to drawing the free body diagram of this one, free body diagram of this one, and trying to eliminate a lot of unknowns here and then simplify this one. So this is just one relationship. Okay. So I'll continue this one in our next class.